Calorimetry, the final lesson on the energetics topic. A little reminder, an endothermic reaction, remember, absorbs heat from the surroundings to the system, so the surroundings get colder, and an exothermic reaction releases heat from the system to the surroundings, so the surroundings are hotter. That's just a little recap. Now, calorimetry, you should be able to describe how you can measure the energy change and the enthalpy change of a reaction, any of these types of reaction. So for combustion, we use this method. For the other ones, such as displacement and neutralization, we use this method. So let's start with displacement and neutralization. What you do is you get yourself a polystyrene cup. A polystyrene cup is used because it's a much better insulator than glass. You put your polystyrene cup in a glass beaker so it doesn't fall over. You fill it with a known volume of water, and then you stick a thermometer in it and wait until you can have that initial temperature. So you maybe wait 2 minutes to make sure the temperature is stable. You then add your solid. For example, if you're dissolving a solid, or if you're doing a displacement reaction, you would put your first solution in, then you would add your solid. So for example, copper sulfate, and then you add zinc. If you're doing neutralization, you would add the acid first, or the alkali first, measure the temperature, make sure it's stable, then add the other one. Then you immediately close the lid and you stir, and you wait until you reach your maximum or minimum temperature. So temperature can either go up for exothermic or down for endothermic. So in the case of combustion, it'll go up, displacement, it'll go up. For dissolving and neutralization, it can go either way. For neutralization, it usually goes up unless it's a hydrogen carbonate. Okay, now, after you reach the maximum or minimum temperature, you write that down, and therefore you'll have something called delta T, the temperature change. Then you'll be using an equation that you will see in a minute of how to use. But the main thing is how to get the temperature change. That's the objective of this practical. The rest of it, I'll explain it in a minute with the equation. Now, the other one you have to know is for combustion reactions. So for example, this is a spirit burner. So it contains an alcohol and is being burnt. What you do is you put a known volume of water in a beaker. You put it on a tripod gauze. You measure its initial temperature at the beginning. Then you get your spirit burner. You measure its original mass. Then you start burning it. I would burn it for about enough time that the temperature rises by at least 10 degrees. Okay, it doesn't matter if you've heated it too long because everything will be proportional, but I would say at least 10 degrees rise. Then immediately close your spirit burner with a cap. That will then extinguish the flame because it'll stop the oxygen going to it. So you've written down your maximum value. You've minus the initial value so you can find the temperature difference. Then you take your spirit burner back to the mass balance. So if you measure it originally with the lid on before you burnt it, and you measure it with the lid on after you burnt it, it will get less in mass because some of it would have been burnt. And that difference in mass you need to write down as your mass. Now, how to actually calculate it? What you do is you use this famous equation, Q, energy change, equals mc delta T. Now, the Q is the energy change and it's in joules. If you want it in kilojoules, you have to divide it by 1,000. The delta T is obvious, is the change in temperature, which is done by doing the initial being taken away from the final. Now, M stands for the mass of your solution. So the mass of your water. Because the density of water is 1, if you have 20 centimeters cubed of water, you would have 20 grams. So you treat the centimeters cubed as grams. The most common mistake here is to put the mass as like, I don't know, the alcohol of the spirit burner that you burnt. Or maybe you put 3 grams of zinc into the copper sulfate and you start putting 3 as the mass. That would be totally wrong because the mass is the mass of the solution. If it's an acid and an alkali, you must combine the two volumes. So I have 25 of acid and 25 of alkali mixed. my mass would be 50. Lastly, C is called the specific heat capacity that's given to you in the exam, and it's 4.2. Okay, its units are joules per gram per degree, which basically means how much energy is needed to raise 1 gram of a particular, how much is needed to raise 1 gram of water by 1 degree Celsius. So the bigger the number, the more energy you need, the harder it is to raise. Because all the solutions of acids and alkalis are done in water, that's why we assume density is 1. So we treat the centimeters cubed as grams. Let's have a look at 2 examples of this Q calculation. 1.24 grams of magnesium was added to hydrochloric acid and the temperature rose. What is the energy change? Well, do not put this as the mass. That is not the mass of the solution. The mass of the solution is the 25 centimeters cubed because density is 1. So my mass is 25, my C is 4.2, and my delta T is the difference between these two. When you multiply them, you get this as the energy in joules. This again emphasizes don't use the magnesium. Next question. 200 centimeters cubed water is heated by burning an ethanol spirit burner. I automatically know my mass is 200 because that's the mass of the solution that we're heating and measuring the temperature of. The temperature difference is 26.8 minus 20.5, and C is 4.2. These masses are irrelevant for the heat energy change, but they will be relevant when we do the molar enthalpy change. So for now, you just multiply MC delta T, and you get your answer in joules. The next stage is to calculate delta H, which is called enthalpy change. Now, the units of enthalpy change are going to be kilojoules per mole, so kJ/mole. As the unit implies, it will be the energy divided by the moles of whatever you've reacted or burnt. So suppose we're doing this one, the ethanol spirit burner one. So if I scroll up a bit. The initial mass was 145. Then after you've burnt it, the mass decreased because it was burnt and it formed this much. So now you can actually use that mass and make a difference because that will be your mass of fuel. Then what you do is you find its moles because we have to divide by moles. So we need the moles of something. So we do mass over MR. Ethanol happens to add up to 46. It's C2H5OH. So it's 12 times 2 plus 6 times 1 plus 16. And it is 46. So we get this for the mole. Now to get into kilojoules per mole, we take this number, we divide it by 1,000 first to get it to kilojoules, and then we divide it by moles, and that will give us an answer in kilojoules per mole. But we're not done yet. Enthalpy change, unlike energy change, requires a sign. Now, plus means endo, like we've talked about before, and minus means exo. Okay, we did talk about this before. So because the temperature seems to have gone up from 20 to 26, we must put a minus in front. So that'll be your final mark. You must have the correct sign. So if temperature goes up, put a minus. If temperature goes down, put a plus. A lot of information, but what you need to do is practice. So I'm going to kind of go over two examples. And I'm also going to tell you a little short summary of this, just to show you that the steps are actually quite simple. So it's MC times delta T. M is the mass of the solution, not the solid. To find enthalpy change, you do Q over N. So capital Q, I've put lowercase q, it doesn't matter, is this divided by moles. But first you divide this by 1,000. Okay. This actually, here there's a misprint. Positive means endothermic, temperature decreased. Negative means exothermic, so I need to fix that for you. But the main thing is Q over N. Now, if we look at 2 examples, actually one main example I have lined up for you is here. This is taken from an actual paper. So it says, complete the word equation. Metal plus acid makes magnesium chloride plus hydrogen. So salt plus hydrogen. Then it tells me to read off the temperature reading here, the start of the experiment. So let's have a look. So it goes 20, 21, 22, 22.2, 22.4. So it's 22.4 at the start. You always put 1 VP for these, by the way. Even if it's 20, you would put 20.0. Now, the highest temperature reached, if the temperature rise was 20.8, we need to add these two numbers together. So we're going to get 2, 3, 43.2. Okay, so that's the answer there. Show that the heat energy changes around this. Now, this is our chance to use our formula. Q equals mc delta T. M is mass of solution, which is 25. So 25 times C, which is given to us as 4.2, times temperature, right, which is 20.8. Now, if you times these two, if you times these numbers together, I'll pop into my calculator, 25 times 4.2 times 20.8, I get an answer of 2184 joules, which is approximately 2,200. The next step, I don't know why it's 4 marks, they just want it in kilojoules per mole. So what you do is you divide that by 1,000 first to get it into kilojoules. So you get 2.184 kilojoules. The sign is not important at this stage, only at the end. They even tell us. Then you got the mass of the magnesium. So mass over MR, which is 24 for magnesium. So always remember moles equals mass over MR. Very important formula. So we get the moles as 0.005. Then to get into kilojoules slash moles, we just divide these two. Okay, so 2.184 divide 0.005, and we have an answer of 436.8, which is 437, 3 significant figures. And for the sign, because it went up, it must be exothermic, which makes it negative. So in essence, you multiply 3 numbers, you divide by 1,000, and you divide by moles. And you stick a sign in front of it. I suggest practicing this with worksheets attached, and that completes the energy topic. So thank you and see you next time.